and welcome to the Chemistry Academy. In this video we're going to go over the theory behind thermodynamics in the Advanced Higher Chemistry course. I'm not going to do any of the exam type calculations in this video. I'll do that in a separate video. For this one it's more just to do with, like I said, the theory behind the thermodynamics and the equations that we use when we are doing the calculations. So to start off with, I'll just introduce you into all the different variables that are involved in thermodynamics calculations. So we have the standard enthalpy change, so that's something you learned about at higher chemistry, where we're looking at the heat energy change within the reaction, and that's always given in kilojoules per mole in chemistry. If you do physics you might see it in joules per mole more often, but in chemistry we always have the enthalpy change in kilojoules per mole. Then we have the standard entropy change. So entropy is a new concept to you at advanced higher level, and it's essentially the measure of disorder. So if you think back to when you were in first year and you learned about solids, liquids and the gases, you may have been lucky enough to get to go and run around like a mental gas particle, and you and all your classmates would have been extremely disordered as a gas. You would be running about everywhere, whereas a solid, you were made to stand next to each other in nice uniform lines, so you were very ordered. That means that gases have high entropy and solids have low entropy. So that's just something to bear in mind. We'll come to that in a couple minutes again. But what you need to watch out for when it comes to entropy change values is that in chemistry we usually have it in joules per Kelvin per mole. The problem then comes for when we do calculations, we need to usually put it into kilojoules, because delta G and delta H are also in kilojoules, so it needs to match up. So just watch out for the units of entropy. Make sure if you're needing to use it in a calculation that you give it in, change it into kilojoules first by dividing by 1000. However, if you're asked to work out the entropy change for a reaction, it's usually asking you to give it in joules, so just keep it in joules if the question's just asking you to calculate entropy. And then we've got Gibbs free energy change. So this is just a value that takes into consideration the enthalpy change of a reaction and the entropy change of a reaction and the temperature, and can essentially tell you if the reaction will be feasible or not. It's in kilojoules per mole, which, like I said, is why we need to then watch out for when we put in the entropy change into our equation. We need to make sure that gets converted into kilojoules. Then we've got also the temperature, and temperature at advanced higher we now look at on the Kelvin scale. So 0 degrees Celsius is 273 degrees Kelvin. That value is actually the very back page of your data booklet, but more often than not we tend to use room temperature, which is definitely not room temperature in Scotland, but it must be room temperature somewhere. Standard temperature, which is 298 Kelvin. Anytime you are converting from degrees Celsius to Kelvin, all you have to do is add 273 onto the Celsius value. So if it was 30 degrees Celsius, you would just add 30 onto that, so it would be 303 degrees Kelvin. Hopefully that quick maths was correct. So that's the variables that we look at when we're looking at thermodynamics. In terms of what you need to consider about all of these, so when it comes to enthalpy change, again, you did it last year. If the overall enthalpy change is negative, then that's an exothermic reaction. If it's positive, then that's an endothermic reaction. With entropy, if there is a decrease in entropy, that means something's becoming more ordered, so it's becoming more like a solid. If there's a positive entropy change, it means things are becoming more disordered, so they're becoming more gaseous normally. So it's always a good idea sometimes in multiple choice questions that ask you about entropy changes, just have a look at the state symbols and see, right, is stuff changing to become gases or stuff changing to become solids, because that's going to tell you which way the entropy is going to be changing, if it's going to be increasing or decreasing. So just remember, gases, very disordered, all over the shop, so they're the ones with a higher entropy. Then we've got Gibbs free energy. If the Gibbs free energy change is negative, that means your reaction is feasible. If it's positive, it means it's not feasible, your reaction is not going to work. So you're either going to need to change the temperature or just do a different reaction. When it comes to entropy as well, I think I've already mentioned this already, but you do get quite a lot of questions on like identifying which substance has a higher entropy or a lower entropy. Just remember, the highest entropy is for those substances that are most gaseous, so they evaporated, they're more evaporated, more spaced out. The lowest entropy will be the ones that are most solid-like, because then they're all uniform and nice and neatly arranged. Okay. The other thing actually you need to remember as well is one of the laws of thermodynamics is that the entropy of a perfect crystal is 0 at 0 degrees Kelvin, which is the temperature that's known as absolute zero. So that's just something you need to remember as a fact, because you do get that asked in multiple choice questions sometimes as well. Okay, so that's the general introduction into all the different variables involved in the thermodynamics calculations. If we then look at the equations that are used in the calculations, so when you're asked to calculate enthalpy change, or entropy change, or Gibbs free energy change, sometimes if you're given data on it, then you would use the sum of the products minus the sum of the reactants, and that is on the equations page of your data booklet. One thing to remember for this is just to remember to times the enthalpies or the entropies by the number of moles of that substance in the stoichiometric equation. That's one thing people tend to forget to do, so don't forget to do that. Then the other equation we've got is the Gibbs free energy equation. So this is what you normally use to calculate the Gibbs free energy. This one just crops up sometimes. In the exam papers you'll see that quite often data is given in tables, and normally it's enthalpy change and entropy change for the reactants and the products. However, sometimes you'll be given enthalpy change and the delta G, or the entropy change and the delta G. So if it is in the table format, this is where you would use this equation here. But most of the time, like I said, the Gibbs free energy is getting calculated using delta G equals delta H minus T delta S. Most of the time the temperature will be given to you in the question in Kelvin, but if there's no temperature mentioned, just go with standard temperature, which is 298 Kelvin, so 25 degrees Celsius room temperature. So standard temperature and pressure is 1 atmosphere of pressure and 298 degrees Kelvin, and that's what these wee circles just mean, is that it's the standard. So at a standard temperature and pressure is what we're calculating. In terms of this calculation, you'll be asked to use it to calculate Gibbs free energy, so in that case you just plug in your numbers, but again make sure that your entropy change is converted into kilojoules, okay, when you do that, and then you plug in the numbers and just solve it for delta G. But you could also be asked at what temperature a reaction just becomes feasible. In this case we make delta G equal to 0, because when delta G becomes negative, that's when the reaction is feasible. So we know that the point that it's 0 is like the pivotal point, and so we on one side of that temperature that the reaction is going to be feasible. So we make delta G equal to 0, and when we make that 0 in this equation, we can rearrange it to T equals delta H over delta S. So this is just something you can memorize if you want to. And then all you do is plug in your enthalpy change and entropy change, and that would give you out your temperature that you need for the reaction to become feasible. Again, just make sure that you convert the units of entropy change to be in kilojoules per Kelvin per mole to match the kilojoules per mole for the enthalpy. And again, I've put the reminder here again, because you won't believe how many times people forget to do that. The other questions that you get that can be quite tricky around the theory behind the thermodynamics laws is these multiple choice type questions that they ask you, like, in which case will the reaction always be feasible, or in which case will the reaction always be exothermic. So it's to do with the relationship of this the variables in this equation. So if we look at when it will be feasible, so we know that for the reaction to be feasible, I'll just write the equation down, that delta G has to be negative. Okay, so the only time where we can ensure that this is negative is if the reaction is exothermic, so that's negative, and the entropy is positive, because then you're going to have a minus minus a positive, so you're going to be subtracting from a negative, so it's going to have to stay negative. Okay, so for the delta G to definitely 100% be minus, we would need an exothermic reaction that is having an increase in entropy. And an increase in entropy is always required for a spontaneous process, so if the entropy is not increasing, the reaction will not be spontaneous. So that is essential for a spontaneous process. Okay, because the universe likes disorder, so if something's increasing in disorder, it's going to be a spontaneous reaction. Entropy is a bit different because there's not as much of a preference around that, although exothermic reactions are probably more favourable than endothermic ones, just because the universe would rather things be in a lower energy state. Okay, so that's the requirements for the reaction to always be feasible. The reaction would be exothermic and the entropy change would be positive. In terms of when the reaction will be exothermic, so that's when we want delta H to be negative. So because the exothermic is to do with entropy change, I'm going to rearrange the equation to have delta H as the subject. So I take that across and it becomes delta G plus T delta S. So we want this to be exothermic, we want it to be negative. Put the brackets around, it makes it a bit easier to see what's going on, I think. So in order for this to be negative, we would need this to be negative and also this to be negative, so that we're adding two negatives. Because if either one of them was positive, we can't say for sure that it's going to end up as negative because we don't know how big this number is, we don't know how big this number is. But if both of them are negative, they would have to add to give you a negative number. Okay, so if delta G and delta S are both negative, then your reaction must be exothermic. So you will get multiple choice questions like this every so often, and it will ask about a certain thing. So it might be even asking you about something to do with entropy. Just rearrange the delta G equation to have the thing that's been asked about as the subject, and just see if you can work out, like, right, does this, if this is plus and this is minus, what would this value end up as? And you have to try and work it out that way. So you have to kind of be quite good at rearranging equations for that, unfortunately. So that is my introduction, whistle-stop tour to the thermodynamics theory. Like I said, I will do some example calculations from past papers in other videos. But yeah, for now that's it. So if you find this helpful, please give it a like, don't forget to subscribe, and I'll see you again soon.